pleasure to speak at this meeting, and it's nice to be the last one, so I can cut a number of introductory slides because we work all in the same field. But also you will clearly see the difference between the academic talk and the industrial talk, as we do have many more technical details. And before I run out of time, so let me acknowledge a number of people who contribute to the work I'm talking today, primarily members of my lab, extensive network of collaborators, a group of Adrian Roiber, University of Florida, a group of Frank Leifert at UNC Chapel Hill, funding mostly Office of Naval Research and National Science Foundation, and a lot of agencies that provided supercomputing and GPU resources, because many of the projects we involved requires a lot of computational time. Now, and you've seen the amazing progress of the AI, but also a lot of hype. And therefore, as the way of introduction and kind of nice segue from the couple of talks before, if you see for the news outlets of this, for example, news for the Royal Society of Chemistry, wanted synthetic chemists, humans need not apply. Or the point that here at ACS, so this is chemical engineering news about the rise of the smartish machine. So you see all the kind of hypey titles. So I'd like to motivate and kind of start my talk with this amazing but thought-provoking quote attributed by Derek Law. If you do not know, Derek writes amazing blog in the pipeline for the Science Translational Medicine. And what Derek said, it is not that machines are going to replace chemists. It is that chemists who use machines will replace those that do not. I think this is, again, very interesting thought from him, especially being, very skeptical about the AI and technology. But I think it's a great motivation to, what is currently happening in the field. And for me, as a computational chemist by training and the focus of my lab, things what are happening right now is really revolutionary, because one of the visions that I share and believe, and many people probably in this session, is that we want to use AI and smart machines to predict, synthesize, measure, test, repeat, and basically have this closed loop system. And the dream of essentially AI-driven molecular discovery, maybe in the real time. And you can imagine that some kind of machine or chemical AI would come up eventually with a hypothesis with the molecule. Then we can output the recipe, and the molecule can be synthesized in the by the robotic system, and then you connect it. In biological and kind of drug discovery sciences, this high throughput biological screens, material science that might be analytical characterization of the material, and then you close the loop and inform your AI, about success of the failure, right? And many lab and companies work, in these directions. And I think about this problem as all of us, we build in this tower, but each of us work on this small kind of a piece of Lego block and all kind of a small module, but together we advance in the science. So for today's talk, I'd like to share two stories, one short story and one longer stories about two of the Lego blocks as it been done in my lab. And I start again with the motivations that many projects in the design of molecules or materials use, essentially the industry standard DMTA cycle, so design, make, test, analyze. And, the scientist comes with the idea, draw a molecule on the board, then you have to synthesize, or somebody has to synthesize it for you, test the hypothesis and, analyze the results, right? So this is de facto how we work, essentially the hypothesis generating science. And one of our efforts in that, can we automate the science, this cycle, and make it faster and probably more efficient, because sometimes the design and making and test, separated a quite lengthy time frame. Now, again, we work in the very difficult conditions of the ongoing pandemic. So robots and automation are really welcome in here. And so this particular application we've done is a design of polymers for the purpose of fluorine-19 magnetic resonance imaging. So we go to the doctor and do your MRI scans. So the imaging, the contrast agent, this is what gives the the bright of the signal. And this work is collaboration with the group of Frank Lepford at UNC Chapel Hill. And so what Frank challenged us to do is to design this, contrast high intensity polymer. And this is one of example of such of the family of the polymers. And it's a good test bed because it's easy to do controlled synthesis. However, still very large space of the design, because you can have different types of the monomers to make your polymer. For example, the fluorine containing monomers that give the intensity, or other type of the monomers that gives other properties, for example, solubility and so forth. And therefore, can we make it happen, and can we automate design of that material? So our solution was twofold. On the Frank side, they built amazing flow-based synthesis, essentially robotic synthesis that there's an example of this photo of the system, a lot of pipes and syringes that takes your desired composition, run the experiments, separates them and so forth, right? It's and goes for evaluation. On our side, we designed this little brain, a machine learned system. In our particular way, we combine active learning cycles with what's called automated ML or AutoML. And the reason for that is that whenever you build machine learning models, a domain scientist is required to select or what kind of machine learning models to use, what featurization to use, and so forth. And therefore, combining AutoML essentially automate and democratize access to this technology, therefore makes automatic decision for you. And then active learning used to screen possible chemical space and outputs what set of experiments to run, next batch of experiments, and essentially outputs the recipe for this robot. So we can close this loop. Therefore, you can now comfortably run this experiment essentially from the comfort of your home. And for this particular application, we use the simplest possible multi-objective optimization. We control two properties. One is the intensity of the signal, what's called SNR, signal to noise ratio, intensity of the MRI signal. And second is solubility, because again, if the material is insoluble, it cannot do the job. And this, again, two properties to control, simplest example of multi-objective optimization. Now, how we approach the problem. We pick 6 types of the monomers, so our problem is 6-dimensional. If you think about the possible space of experiments to run, given how we can control the composition, so the total experimental space was about 50,000 experiments if you want to exhaustively do all type of the materials. Therefore, it's clearly this is not possible to run and not necessary. So we approach this problem with hierarchical exploration. So we can do first a coarse exploration of the chemical space using the larger step in the composition of the monomers that give us space about 2,500 polymers, and find small step that again 45,000 experiments. On the right, you see UMAP projection of the chemical space. So points in red is our coarse steps. Points in gray, that's our fine space. Overall, kind of a teaser, what we did less than 400 experiments, which is 0.7% of all possible space. And by that point, we already designed actually a dozen of the best-in-class polymers and improved the intensity about 50% to what is known state-of-the-art before. Now, let me show you how it's working temporarily. In temporal dimension, overall system runs in batches of 30 or so experiments. We run 8 batches of the experiments. over over this project. The batch 0 was initialized with essentially all experiments been done before, when the system was tested and built, and also a lot of chemical intuition from the polymer chemists, PhD student in material science, who tried to design the polymer essentially with the human intelligence. So it's a busy plot. Let me walk you. So we have our 8 batches of experiments. So the top panel shows you the mean absolute error of machine learning prediction of our target MRI properties. This bunch of points on the bottom indicated the insoluble materials. So essentially, when material became insoluble. On the right, again, this is the full chemical map colored by the prediction of the machine learning models. So what we run several steps of the active learning in the course space. And then we attempted essentially exploiting, greedy selection of the best possible materials. And at this point, interestingly, system failed miserably. All predicted materials were insoluble, as indicated by this lots of points here, and therefore, we failed to produce, any meaningful material, which again, kind of says what Ola mentioned, predicting solubility is a challenge. Therefore, the quality of the solubility model was not good enough. Then we switched to our fine chemical space, ran several more iterations, and as you can see, machine is getting better and better, and overall, designing materials with higher and higher properties. And by the batch 8, we attempted one more exploitative step. And by that time, we actually found several of these record-breaking materials. And we also identified several interesting regions of the chemical space where this top-performing materials are located. Long story short, we can also, using this approach, we can also monitor and kind of look what's the model belief about the interesting and the favorable regions of the chemical space. So again, it's our full chemical space. With open dots, there's actual experiments been done in this particular batch, and we can see and monitor the changes how machine learning model believes and where it explores. First it think the hot colors corresponds to more interesting regions. It think this particular island of the chemical space is very favorable, so explores, and eventually it kind of give up because it's not that good. But otherwise, this particular island, very screaming red, and therefore kind of concentrate on exploration here or on this island, and therefore we can monitor how what is the predicted and interesting regions in the chemical space. And overall, what this kind of maps give us is appreciation how complex this problem is. Even our simple design of these experiments and only 2 properties, so obtaining the structure composition property landscape, is extremely complicated. So again, this is our map. On the left panel, we color-coded by predicted the signal intensity, and on the right, a predicted probability of water solubility of the material. And you can see obviously that regions of high interest are red. This is where model thinks the materials are insoluble. And if you zoom in into one of the particular island of the high interest where the top materials were found, you see actually very complex landscapes where pockets of soluble and insoluble materials actually are kind of on top of the most promising regions. And therefore, what we found in this simple exercise, that eventually the materials that were designed and the top performing materials were very non-intuitive. So the highest performing material was not the materials that have higher percentage of fluorine and therefore high intensity, because again, the problem is the solubility, and therefore design of any material or a molecule is the multi-objective optimization. So overall, for me as computational chemist, so life achievement, we can run a robot from the comfort of our home, and therefore this automation is actually what allow us to do this experiment during this, very difficult time of the pandemic lockdown. We developed the ML, kind of after ML based methods for semi-autonomous polymer design, and overall this method is generic, and we plan to apply it to other experimental problems. As you can see, even simple multi-objective optimization result in very complex composition landscapes, and therefore we need better methods to explore chemical space. And overall, in one short experiments, we already developed number of best-in-class materials with two desired properties. Now that's a summary of the story one. Now for the main story, and this is the main activity of our lab, is how machine learning can help us to develop better, more accurate computational chemistry methods to better serve in the design of molecules and materials. And overall, the whole history of computational chemistry is driven by this problem. Should I use fast and approximate method or more accurate but slow? And therefore, we see whole number of different methods, starting from classical molecular mechanics and the force fields, use very simple analytical terms in terms of the bond angles and non-bonding terms, essentially model of atoms as the strings and the balls, or do solve Schrodinger equation and have rigorous description of the quantum nature of the molecules. And overall, you can represent essentially as this kind of a ladder in two-dimensional space. When on x-axis, we have computational scaling of the method versus some kind of metric of accuracy. So my interest in to do protein ligand simulation, I'm probably stuck here in this low left lower corner, and have to rely on the force fields that are kind of linear scaling methods, scale with the number of atoms in the systems. It's not the problem that force field could not be accurate, but the problem is that uncertainty, sometimes it's high. We do not necessarily know when they work very well and how to systematically improve it. So to reduce this uncertainty, we have to climb this ladder and maybe go to semi-empirical tight binding methods, and reduce this error, intensity functional theory, and finally for organic molecules, couple cluster theory. CCSD parenthesis T is considered the gold standard, provides you an accuracy about within 1 kcal per mole from the high accuracy experiment. The price you pay is 7 order of scaling with the system size. Therefore, this only accessible to run smaller molecules. And for the computational chemist in the audience, so this is the heaven. If you need the exact answer, so full CI with complete basis set gives you virtually exact answer, but it's unpractical for anything, with the exception of the hydrogen molecule and so forth. And therefore, the promise of the machine learning methods is combine of the both, best of the both world, right? So machine learning potentials, as we call them, have linear scaling and speed approaching the force fields, and given proper training on the accurate computational chemistry methods, things like the functional theory, you can approach and push the boundary of these methods to the top left corner. Therefore, this is exactly what we're trying to do for past 6 or 7 years. And again, why we can do it? So this is my time-independent Schrodinger equation. And again, we use large machines to solve it numerically. Therefore, it's that expensive. But if you look at this equation as the data scientist, my energy, and if you rearrange the equation, my energy would be this black box magic function f, depending on molecular coordinates. And this is a supervised machine learning. This is a regression problem. and we use neural networks to solve this problem. So we feed molecules to a neural network to compute energy. And the beauty of neural networks, that's why we like them, they're fully differentiable. You can backpropagate, you can get energy. In addition to energy, you get forces. You can also do second derivatives Hessian, and therefore you can do practically all types of simulation as with traditional quantum mechanical and molecular mechanics methods. And therefore, over the years, we developed several of those machine learning force fields. And first of our efforts, what's called ionizing neural network. And to my knowledge, this is first machine learning transferable force fields. And by transferable, it's mean you train it once, and then you can apply it to practically any type of organic molecules. You know, if you're interested in technical details, this is a reference. But it's been extremely successful and provide accuracy within 1 or 2 kcal per mole for many types of and classes of organic molecules. But the training for this neural network would primarily focus for a kind of drug-like organic molecules. Let me show you a little bit how it works. So in the core, why and how it works, we rely on the principle of near-sightedness of chemical interactions. That, you know, you've seen these types of graphs, that interactions between, you know, atoms or molecules have, you know, the shape, and as you can see at certain distance, you know, this particular type of interactions approaching to 0, and therefore you can truncate this interaction and put a certain cutoffs and make the approximations. However, as always, there's a star to that principle, and therefore, you know, as you may know, there are long range and other types of interactions that cannot be truncated. But for you know, for many types of molecules, this assumption is quite valid, and therefore, what we can think our molecule and represent it as the set of descriptors where each atom inside the molecules characterized by what's we called atomic environment or asymmetry functions. And essentially, this is a sphere up to our cutoff radii, as it encodes this atomic neighborhood of this particular atom and the molecules. This idea goes back to the pioneering work of Beller and Parinella, 2007, and in our work, we adapted this idea for organic molecules, and therefore, you know, the idea is the same, but, you know, in our implementation, it has slightly different mathematical formulation. And again, if you're interested in equations, it's in that paper. And essentially, what your neural network doing is zoom in at this environment at a time, and your energy of the molecule is going to be sum of these atomic environments. Now, how we train it? Again, you record a database of your molecules, compute quantum mechanical energy and properties, take your molecule, you featureize, compute this atomic environment for every atom in the molecule, pass it through a neural network, sum them up, and compare to a reference quantum mechanical energy. You know, look for the error, compute cost gradients, update neural network, you iterate, and essentially this is how your typical neural network can train for any purpose. At the inference time or a simulation time, this is essentially a black box energy functions that you can plug it in to your favorite simulation package. You feed molecule in, you compute energy, you backpropagate, compute forces or Hessian. Therefore, you can do any type of simulations. At the moment, we parameterize essentially all biogenic elements. So if you draw me a molecule with that, you know, 7 elements, will give you energy and forces. We progress essentially adding more elements, and we have a prototype of 14 all non-metal elements done. For computational chemists in the audience, is our choice of particular combination of DFT functional with the basis set. We also have a couple cluster trained neural network for extremely accurate thermochemistry calculations. We apply us and, you know, other labs apply it to a variety of different applications. So there's a couple of examples from our lab. again, where is beneficial, this force fields provides you very accurate description of geometry and potential energy surface for organic molecules. So this plot on the left gives you several typical examples of molecules that are traditionally hard for classical force fields, molecule with sulfur, a lot of halogens, therefore they're polarizable. However, out of the box, these molecules, for a particular set, what I'm showing here, we selected a couple of dihedral angles and built potential energy surface, essentially varying these angles at the molecules, built in this potential energy surface map, quantum mechanical solution on the right, from the neural network on the left. And as you can see, you can hardly see the difference, even these little kinks in the potential energy surface are very well learned, and therefore gives you accurate description, again, within 1 or 2 kcal per mole. Additionally, also try it on gas phase reaction thermochemistry. You can compute, again, energy of reaction, free energy of reactions, and again, is very well compared to high-level quantum mechanical calculations and experiment. Again, if you're interested, there's the details in the references. Next frontier, as Ola mentioned, is combining and approaching more complex problems. For example, free energy simulation of protein ligand binding. This is our attempt. We use TYK2 kinase, and it's one of the examples of the high quality binding free energy that's been measured for a congeneric series of molecules. And therefore, we combine our neural network potential with traditional force field-based simulation to compute protein ligand binding free energies. And again, what we see that it really helps reducing the uncertainty and improve the accuracy of free energy simulations. For example, if you're interested to compute absolute binding free energy, so on the left is comparison of state-of-the-art force field-based simulation experimental binding free energy versus computed, again, through through thermodynamic integration or perturbation theory. So this is kind of a correlation you will get. Despite the fact that errors in the free energy is 1 kcal per mole, you see the R square, so the ranking is not very good because you see several molecules essentially as an outliers. Out of the box, replacing only the part of the simulation, only the ligand with the ML potential, reduce this error by 50%, R square from 0.4 going to 0.86, and therefore we can substantially reduce the number of artifacts. And this is a preprint of this practice work. Now, all of this implemented in our software ecosystem. It's open source and based on the PyTorch. It's written in Python. It's a link here on the right. It implements a number of different types of simulation. Molecular dynamics, geometry minimization, thermochemistry, conformational search, and so forth. Take advantage of running on the GPUs, therefore the simulation are blazingly fast. Now I'm stepping up in the kind of a danger zone, and I'm going to show you some code. But hopefully you will see how easy to use in Python. For example, you read your file for particular here. It's a water molecule. You initialize the calculator. You can compute energy. You can do geometry minimization. And as you can see here, geometry minimization takes 17 milliseconds. So it's blazingly fast. You verify that after your optimization, your forces are very close to zero, and you can do all types of simulation. So there's another example. You can do vibration analysis and get essentially a correct answer that water has 3 normal modes, and you can do full type of chemistry within a fraction of a second. So therefore, it gives you access to accurate quantum mechanical level simulation. But 1,000,000 times faster. Again, I can think about the problem we saw here and designed the neural network architecture, again, building these Lego blocks, but now we essentially designed the architecture and type of the layers in the neural networks. And therefore, we work and develop a number of such architectures. So here's the list of several architectures that we designed so far. It's a busy slides, but let me walk you through it. What we indicated in yellow, those are input of molecular coordinates and prediction of energy or properties. Things in blue, those are mathematical transformations. So we take molecular coordinates and transform into atomic environment, so descriptors. And what is green, those are building blocks of neural network. Again, I unfortunately do not have time to describe all of them in details, but references are here. But you can appreciate that we started from the simple neural network and have fun playing and designing different architecture. Particularly here, one on the right, it's approaching kind of a physics-inspired artificial intelligence, where the neural network actually predicts several diagonal and off-diagonal elements for the model Hamiltonian. In our case, was extended Huckel model. And therefore, we can use this very simple model to predict energy and orbitals for molecular system with the accuracy approaching of DFT. Overall, if you're interested to learn more, we just published this, a paper in Accounts of Chemical Research that describe our journey for past 5 years. And therefore, if you're interested in details, I encourage you to read it. But let me show you just a couple of things, how can improve this architecture and maybe combine physics and machine learning in a better way. Again, if you go back to our original work with any architecture, it's very simple. You take your molecular coordinates, compute atomic environment, pass through neural network, predict the energy. And therefore, if you remember my comment about the truncating of the long-range interaction, that's exactly happened. How can we improve this architecture and include long-range interactions? Or is our descriptor is really optimal or not? And therefore, we come up with this architecture. We call it AIMNet. And the reasons were the following, right? Instead of us crafting this atomic environment and finding the best equation to represent it, let's make this embedding learnable, and therefore let neural network learn the best optimal descriptor itself. Let's also improve our architecture by getting this additional layer and essentially what we call it neural network, adding the message passing mechanism. So that would essentially in neural network passing the messages, but in reality, this is the mean how to describe long-range interactions and pass this interaction from environment at a time, and therefore essentially mitigating this limitation. And this is how AIMNet architecture was born. And the AIMNet stands from atoms and molecules neural networks. And the inspiration is clear by the Bader theory of atoms and molecules. In Bader theory, atoms inside the molecules are self-consistent in terms of electronic density. In our case, we have this embedded learned representation of atoms inside the molecule that is consistent with the neighbors in the molecule through the means of this updates. And therefore, this architecture showed to be extremely successful. It's improved some of the deficiencies of original works. This learned representation allow us to do analysis and see how neural network learn representation of the molecules. So again, for set of organic molecules, this is 2D embeddings of 2D representation of this learned atomic embeddings. You can actually kind of interested, you can see this embedding organized how this corner of the periodic table. So we have oxygen and sulfur, fluorine and chlorine, and hydrogen closer to the halogens, which kind of makes sense from the chemistry point of view. You can also zoom in the cluster of the carbons, and you can see different kind of subclustering of the carbon in different types of environment, in the electron donating, withdrawing environment. This embedding also nicely correlate with the partial atomic charge has been computed with DFT, and therefore that might be one of the way how we can open a black box and analyze what this model learned, and maybe do analysis of the simulation with the neural network. We tested this model also with the experimentally observable. So we trained AIMNet to gas phase and also energy in the solvent using continuum solvent approximation as SMD model. And therefore, for example, what we can do, we can go into database that collected, so the database called MNSOL that collects free energy of solvation, and we can compute them fully computationally and compare with experiment. As you can see, it's a decent correlation, and error was only 1.8 kcal per mole. And here this error is actually is just mostly showing the limitation of the continuum solvent, because when the free energy is large, those are mostly dictated by the specific solvation effect rather than other factors. Now we continue to improve that, and we also very interested in the chemical reactivity, and can we learn a chemical reaction? Can we predict transition states? And therefore do simulations, things like IRC and so forth. However, if you notice, most of the current architectures, not only from our lab but many others, have a severe limitations because the descriptor is only geometry dependent. And therefore, if you're interested in different charges or different states, you typically have to train several models for every charge or a state of them. Therefore, is in this very recent work, we extended AIMNet architecture to mitigate these limitations. So we condition a neural network on the total molecular charge and spin multiplicity. Therefore, essentially providing a very generic framework how you can train machine learning potential to molecules and materials in all possible different charge and spin states. And it's done by adding this external additional neural network blocks that predict spin polarized charge and spin charges, and basically condition our energy on the total charge and multiplicity. And this is really all what is required to solve Schrodinger equation, only three things. Let me show you how it works, graphically. So this molecule is a prototypical example how to show you this essentially non-local effects, where we have two conjugated aromatic rings and electron withdrawing and electron donating groups. Now, what would happen if you either attach or detach electron from it? So this is quantum mechanical picture of you. You see, the charge or the electron hole is quite it's primarily localized on the group, but also you see substantial delocalization across this conjugated system. So this is a very non-local effect. If you look for spin charges, the spin charge actually organized as almost as a spin wave. So you see positive, negative, because again of this non-local effect. If you use any type of just purely geometrical descriptor model, the neural network would have very qualitatively wrong prediction, because all of the charges is going to be exactly the same. So including what we call this neural spin equilibration block, passing these messages across the full molecules, as you pass them, as you essentially equilibrate neutron spin and the charges, you see correct appearance of behavior of the spin wave, and therefore this is a mean how you can describe chemical reactivity and this non-local effects of the charge and the state. Now we put this to work, and one of the things that we did, we take this architecture and we train it to 3 different states: neutral molecule, cation radical, and anion radical. From these 3 states, you can compute, for example, quantities as electron affinity and ionization potentials. Will not bore you with the analysis of the accuracy, but overall it's high quality. Errors within 2, 3, maybe 3 kcal per mole for all the 3 states and also the derived properties. However, what this design of this neural network provides us is the following: that now, given access to all these quantities, and we can remember one of the very useful theory that's called Conceptual Dft. And the Conceptual Dft theory allow us to compute various different chemical quantities, global quantities, things like chemical potential, molecular hardness, electrophilicity indices, and also localized on the atom condensed things like philicity indices, Fukui potential, Fukui indices, and all of these indices essentially connected to the difference within energy with respect to the number of electrons, or you can also compute the finite difference approximations for all these quantities. Now, design of this architecture actually allow us to fully bypass quantum mechanical calculation and derive all of the indices just by essentially interrogating neural network, because we can specify different charge states, get different spin charges in different states, and compute all of these indices essentially bypassing full quantum mechanical calculations. It's really great because allow us to use this in practice. Let me show you one application, and this is a electrophilic aromatic substitution reaction, an example of bromination. And this is probably one of the fruit fly of the organic chemistry, where the issue is what is the regioselectivity of these reactions. And for the non-chemist in the audience, basically this reaction is where this bromine substituent will go into the aromatic rings, depending on the R group substituent, maybe here. And overall regioselectivity of this reaction is dependent what's called the stability of the sigma complex, where this the charge can be delocalized along this aromatic rings. So the state-of-the-art methods actually use quantum mechanics. You can either use straightforward quantum mechanics, compute all the conceptual Dft indices, or you combine quantum mechanics and what's called the regioscheme. This is the semi-empirical method that enumerates all possible sigma complexes and therefore allows slightly better prediction. But overall, in this little table, the quantum mechanics can allow you predict regioselectivity with high accuracy, about 90% or so. Out of the box, if we replace these things with AIMNet and compute these indices without retraining, and also add our learned representation for atoms, we can essentially approach the accuracy of quantum mechanics, but million times faster. Therefore, it allows us to access high quality reactivity indices and descriptors for the practical purpose of prediction of outcomes of chemical reactions. With that, let me finish and leave you a number of links. All of our codes are available on GitHub. Again, Python implementation of the ANI. Many of our neural network have been linked in your favorite simulation packages. We have plugins for OpenMM, Amber, NumD, Tinker, LAMMPS, and ADF. So AIMNet also here. So if you're interested, most of our quantum mechanical data is also available. And if you're interested, DFT or couple cluster data to use for your own purpose, it's here. And thank you very much for your attention. I'll be happy to answer any questions.